So a brief outline. So I'll start with an introduction to heat pumps to explain what they are and briefly how they work. Then I'll look at the comparison between different types of heat pumps, and then we'll focus on the air source heat pumps specifically. And we'll look at their performance in cold climates. Then I'll give you some heat pump resources. And afterwards, I'll demonstrate what kind of savings are possible with a system approach, which means when we combine a heat pump with other energy efficiency measures. I'll talk briefly about some financing and incentives. I'll try to summarize some main conclusions, and at the very end, I would like to show you how to use two nice tools or online tools to help you make your own decisions, so you can decide in your own specific situation whether a heat pump makes sense for you and also how to optimize its use. So what is a heat pump? So heat pump is a device that takes heat from a cold place and puts it into a warm place. So that's kind of the opposite of what's happening naturally. So naturally heat flows from hot to cold, but we can reverse it with a heat pump. You all are likely familiar with heat pumps because you all probably have experience with using a refrigerator or a freezer. And a refrigerator is a heat pump. So a refrigerator, it takes the heat from the inside of the fridge and puts it to the outside. That's why the coil on the back of the fridge is hot, because that's where the heat is going. Or think of a freezer. When you have, inside in the freezer, you have, say, 0 degrees Fahrenheit. And the freezer, so the heat pump in the freezer is extracting the heat from the inside of that freezer, so from that, say, 0 degree Fahrenheit environment, and putting it to the warm environment outside the freezer. That's why, again, the coil on the back of it is warm, because that's where the heat is going. So we can use the same technology to heat buildings. So we can extract the heat from the outside. So now, instead of extracting the heat from the inside of a freezer, we're extracting it from the outside environment, but it's actually in Alaska very similar to the environment in your freezer. And so extracting the heat from the outside environment and putting it into the building to heat the building. If anybody is interested in the details of how this really works, the heat pump uses a special fluid that we call the refrigerant. And if I start here, the refrigerant is in the form of gas, and it's compressed with a compressor. So the heat pump needs electricity, because that's what the compressor is using. And so when you compress the gas with the compressor, what happens? It gets hot, and then we send this hot gas into the building, and we let the heat from this hot gas be transferred into the air in the building. And so as this refrigerant is supplying the heat into the building, it's being cooled down, and as it's being cooled down, it condenses from that gas into a liquid. And then we send that liquid to the outside, so this is the refrigerant liquid form, into what we call the evaporator, and we let it evaporate in that evaporator. And through evaporative cooling, the temperature of it actually drops below the temperature of the outside environment. And so then the heat from the outside environment is flowing into the refrigerant. And then we compress it again, and the cycle continues. So that's in a nutshell how a heat pump works. Now, the outside environment, that can be either the ground, then we talk about a ground source heat pump. It can be a body of water, then we talk about a water source heat pump, or it can be the outside air, and then we talk about an air source heat pump. And that's what I'm going to focus on in this presentation, because that's where most of the interest currently is in Alaska. It is in the air source heat pumps. Here's an example of what they can look like. So this is the outside unit of an air source heat pump. So it's sitting in the outside air and extracting the heat from that. And here is one of the examples of what the indoor unit can look like. And that indoor unit is supplying the heat into the building. So what are the advantages of heat pumps? They are relatively low maintenance. They use no combustion on site. They're partially renewable because the heat is in the outside environment thanks to things like the sun. they can be fully renewable if the electricity for the heat pump also comes from renewable sources, and they have the potential to lower energy use and energy costs, and that's because their efficiencies are greater than 100%. That's why we don't really call it efficiency, we call it the coefficient of performance. Now, how is it possible that it's greater than 100%? It's because of the laws of physics that tell us that energy can be created or destroyed. So the energy that we put into the heat pump in the form of electricity ends up in the building in the form of heat. And the energy that's extracted from the outside environment is also then ending up inside the building. So the amount of energy that ends up in the building is greater than how much energy we put into the heat pump in the form of electricity. Now, how many times greater it is, that's what the coefficient of performance tells us. So the coefficient of performance, if it's, for example, a 3, it means that for every unit of energy we put into the heat pump in the form of electricity, we get 3 units of energy in the form of heat into the building. And that's because that 1 unit of energy that we put into the heat pump in the form of electricity ends up in the building in the form of heat. And in addition to it, it extracts 2 additional units of energy from the outside environment in the form of heat, and they end up in the unit also. They end up in the building. And so again, if the COP is 3, for every unit of energy you put into the heat pump in the form of electricity, you get 3 units of energy in the form of heat into the building. So the Alaska Center for Energy and Power did a great job summarizing information about existing installations in Alaska. And one of the things that they looked at is their installed cost. And so here on this graph on the y-axis, that's the installed cost per 1 unit of thermal output. It makes sense to look at it per unit of thermal output because obviously bigger systems are going to cost more, but this way we can normalize it. And on the x-axis is the size of the systems in terms of its thermal output. And so they looked at various types of systems. And when you look at the graph and look at different dots and different types, they are all over the place. There is no clear conclusion, seems like, that we can draw and say, one system is cheaper than the other system. And it's because there are other factors that play a role in the install cost, because besides just the type of the heat pumps, there are things like how do you bring the source to the heat pump, or then how do you distribute the heat from the heat pump throughout the building. But there is one conclusion we can actually draw from this graph, and that relates to this dot, what looks like a dot, but I'm telling you it's actually 4 dots on top of each other, and they all represent a ductless mini split heat pump. Ductless mini split heat pump means it's an air source heat pump that's ductless. It looks just like the indoor unit I showed on one of the previous slides. It doesn't have any distribution system. It just blows warm air into the building. And as you can see, so this these 4 points here, it is the lowest cost we can see out of all these installed systems. And again, it is because there is no real cost to distribute the heat. There is no distribution system needed. It's a ductless system. And there is no cost to bring the source to the heat pump because it's an air source heat pump. So it just sits in the outside air and extracting the heat from that. And so because of this relatively low install cost compared to the other systems, there is a lot of interest currently in Alaska in the ductless mini split systems. And that's what we are going to be focusing on in this class today, the ductless mini split systems. So the Alaska Center for Energy and Power also looked at their efficiency, which means they looked at the coefficient of performance of some of the heat pumps that they studied. And here again, you have the different types of heat pumps. And when you look at the data points, they are all over the place. It's, again, we cannot just make a conclusion to say one type is more efficient than other types. However, some of the observations we can make here is, and one relates to this blue square up here, which this is a ductless mini split heat pump in Wrangell, Alaska. So that's the highest COP you can see here. So the highest coefficient of performance. It's about 4.5, which is pretty impressive. But unfortunately, we can't just say that ductless mini split heat pumps have the highest efficiency because of this one single point. Because if you look at the lowest coefficient of performance in this graph, it's also a ductless mini split heat pump. So there's this green dot down here. It's a ductless mini split heat pump in Dillingham, Alaska, with the coefficient of performance of about 1.6. So again, we can't just say that one type of a system is more efficient than others. But one conclusion we can draw from here, and it again relates to this blue square up here, is that if we use the ductless mini split systems in appropriate situations, and we use them in an appropriate way, we can achieve a very high efficiency, which means we can achieve a very high coefficient of performance. So now, of course, the question is, so what are the appropriate ways and what are the appropriate situations to use them? And it's something we'll look at throughout this class. So when we talk about air source heat pumps, there's of course a fundamental challenge, and it is that the lower the temperature outside, the harder it is for the heat pump to extract the heat from that outside environment. So the capacity of the heat pump is dropping, while the building envelope does the opposite. So the colder it is outside, the more heat you need for your building. So you end up with a deficit. And at some point, the heat pump stops working altogether when it gets really cold outside. So when you need it the most, your heating system stops working on you. So that's one of the challenges associated with using air source heat pumps. So there is a need for a backup heat source in cold climates because, again, when it gets very, very cold, and there's no heat pump on the market that would be able to continue operating in those conditions. So other considerations, one is what is the source of electricity and its efficiency. So if it's, say, a hydroelectric power plant in Southeast Alaska, it can make a perfect sense to use a heat pump. If it's a diesel generator in rural Alaska, where often diesel is used for heating also, then a fair question is, well, does it make sense to burn diesel in the power plant to produce electricity for the heat pump when you can just burn the diesel on site and an all-fired heating system and heat the building that way? And when you look at the numbers, kind of an efficient diesel generator is, say, 35% efficient. An efficient oil-fired heating system is, say, 85% efficient. 85% divided by 35% is about 2.5. So we need the coefficient of performance to be at least 2.5 in those situations for the heat pump to be making sense. Because if the COP is lower than that, then the amount of diesel that you are burning the power plant to produce the electricity for the heat pump is greater than if you were just simply using the diesel on site in an all-fired heating system. Other considerations are you going to use an air-to-air heat pump or air-to-water heat pump? The air-to-water heat pumps have a significantly higher initial cost. So what we see that most of the interest is in the air-to-air heat pumps currently. For the air-to-air heat pumps, then the question is, are you going to use a centrally ducted system or a ductless system? And again, the most interest currently is in the ductless mini split system, which is what you can see here. Again, the outdoor unit and the indoor unit is ductless. So there are no ducts connected to it. It's just directly blowing warm air into the room in which it is installed. Other decisions you need to make is, are you going to use an external thermostat, or are you going to use just a built-in thermostat for the ductless system? So when you buy the unit, it already has its own temperature sensor installed here on the inlet. So it takes the indoor air, it's sucked in here on top. then it is warmed up inside the unit, and it blows out the warm air, and it only has the temperature sensor installed on top. Or another option is to purchase an external thermostat. The reality is most people don't. Most people just, again, when they are looking at the lowest cost, most people just use the built-in thermostat on the inlet. It's not a perfect situation because some of the warm air that the heat pump is blowing out because of its buoyancy actually ends up on the inlet. So the temperature sensor on the inlet is not a perfect representation of the room temperature, but it's pretty close, and most people are okay with that. So again, most people just use the ductless spin split system with the built-in thermostat. Then an important consideration, of course, also when we are using heat pumps in Alaska is what is the outside air cutoff temperature. Because if we want to use it in very cold climates, we need to be looking if it's even possible with the given heat pump. So how do they perform in Alaska? We did a study in 2014 to 2015, and we did the study in a number of communities in Alaska. Here you can see the dots of the communities where we study heat pumps, and the communities with the orange squares, so that's Dillingham, Juneau, and Wrangell. That's where we studied heat pumps in a greater detail. That's where we did very detailed monitoring of those heat pumps compared to the other communities. And here are the results from those very detailed studies in those three communities. So in this graph, on the y-axis, that's the coefficient of performance. On the x-axis, that's the outdoor temperature. And I should point out that with the coefficient of performance, we not only looked at the steady state coefficient of performance, but we also looked at the integrated coefficient of performance, which is the real coefficient of performance in the real situation when the heat pump doesn't always run in a steady state. Sometimes it's turning on and off. It's cycling, and I'll explain why. And I'll explain on this series, this blue and black series. So this was actually an air-to-water heat pump, air-to-water heat pump in Juneau. And when you look at this series, looking at temperatures, say from 40 degrees Fahrenheit to say 45 degrees Fahrenheit or so, as you can see, the black dots, and they represent the integrated coefficient of performance, right on top of the blue dots, which is the steady state coefficient of performance. So those series are basically the same. And it's because in this temperature range, the heat pump does operate in a steady state. So there is no cycling needed. It's just running. What happens when the warmer temperatures here, say above 45 degrees Fahrenheit or so, what happens is that the heat demand of the building becomes too low. And the heat pump, even with its lowest compressor speed, the amount of heat that it's supplying is too much. And so the only way that the heat pump can deal with this lower heat demand is to cycle. So it runs for a little bit and turns off, runs for a little bit and turns off. And now because of the cycling, as you can see, the integrated coefficient of performance is lower than the steady state coefficient of performance. Now, what happens in the colder temperatures, below, say, 40 degrees Fahrenheit or so? And remember, the coil on the outside unit is colder than the outside environment because it needs to be able to extract the heat from the outside environment. So, when we are looking at these temperatures below 40 degrees Fahrenheit or so, then the coil can be below freezing, and there's condensation on it, which again below freezing is turning into ice. And so the coil is icing up, and when it's iced up too much, the heat pump needs to defrost itself, which means it stops heating for a short period of time. It actually takes a little bit of heat from the inside of the building, which means it reverses its operation, and it sends it to the outside, to the outdoor unit, and so it warms up the outside coil way above freezing to melt the ice on it, but then just drips, goes down and drips on the ground. And when it's done defrosting, it goes back to the normal heating mode. So in the cold temperatures, the heat pump has to cycle because of the defrost. And because of that cycling, again, the integrated coefficient of performance is lower than the steady state coefficient of performance. So this black series that represents the integrated coefficient of performance, as you can see, is below the blue series that represents the steady state coefficient of performance. So so again, the real thing that at the end is going to determine your energy bill is the integrated coefficient of performance. That's the heat pump in its real world operation. One thing I want to point out, and it's about this red and green series. So this was a ductless mini split heat pump in Wrangell, Alaska. And besides monitoring its performance, one thing that we noticed, even though it wasn't the purpose of the study, was that with a lower level of thermal loading, the coefficient of performance was going up. And what I mean by a lower level of thermal loading, just kind of think of sizing heat pumps. So if you have an oversized heat pump that's never going to run at its full capacity, it means it's operating at a partial level of thermal loading. So that's what we mean by that. And so in this case, even at the same outdoor temperature with just changing levels of thermal loading, when the level of thermal loading was lower, the coefficient of performance went up. Unfortunately, we cannot draw any solid conclusion from that, because with this heat pump, and this was a ductless municipal heat pump in Dillingham, Alaska, we noticed the opposite. So that's this blue and purple dot series, we noticed the opposite, that with lower level of thermal loading, the coefficient of performance actually went down. So this kind of triggered a research question that we looked into later, because again, it's important to understand that, to understand how to size systems and how to operate them. So I'll get to later, I'll point it out. But while I'm here on this slide, a few things I want to point out. So I mentioned that the ductless mini split systems can be very efficient if we use them in appropriate situations. So here kind of see, for example, here, that's an appropriate situation. You can see a very high coefficient of performance. So, in relatively warm temperatures, this was in Wrangell, Alaska, in Southeast Alaska. So that's the situation where you can achieve significant savings with the heat pump. Now, looking here, we can see the coefficient of performance is close to 1 actually. It's typically not an appropriate situation to use a heat pump. And remember, in a typical rural Alaska community, which uses diesel for electricity generation in the diesel generator, and also diesel for heating buildings, I explained that we need a COP of at least about 2.5. So here, we are way below 2.5 with this operation as heat pump in this region. So here, the amount of diesel that the power plant is burning to produce the electricity for heat pump is greater than if you were just using the building with diesel in an all-fired heating system. I should also point out that that the efficiency of heat pumps is improving. This is again a study from 2014, 2015. Now the newer models on the market, some of them have a better efficiency. So with some of them we see that they stay above a COP of about 2, above about 0 degrees Fahrenheit. I should also point out that kind of the threshold, I mentioned 2.5 for rural Alaska, but different communities are different. I saw in the poll at the beginning that we do have a lot of people in Fairbanks here. So in Fairbanks, for example, kind of the magic number is a COP of about 2. And it's because you might think, well, we have a coal-fired power plant in Fairbanks, so that's a problem because then when you're using the heat pump, it's basically running on coal. But in reality, it's not actually the case. The reality in Fairbanks, as far as I understand, is that the coal-fired power plant is maxed out. And when you install a heat pump, you're not going to be increasing the consumption of coal because it is already maxed out. What's going to happen is that the combined cycle power plant in North Pole is going to pick up the increase in the load, which is actually a very efficient power plant. And so because of the specific situation in Fairbanks, if you do the numbers, we are looking at the COP of about 2. And it actually applies to both. We are kind of lucky in Fairbanks. It applies to the CO2 emissions, kind of the break-even point, as well as the costs. So So if you can run a heat pump with a COP greater than about 2, you are saving money. When you look at the cost of electricity for the heat pump versus the cost of heating oil that you would be using for heating. So I'm pointing all this out to just again, we have a lot of people from Fairbanks here, to point out that with some of the newer, most efficient heat pumps, you can operate them down to roughly 0 degrees Fahrenheit in a beneficial way in Fairbanks. So some general conclusions from this detailed monitoring. So as you can see, that the cycling of the heat pumps can significantly reduce performance. So optimizing the defrost controls can have a significant impact as far as improving the performance of the heat pumps. And also you saw there's a large variation in efficiency among individual models. So when you are selecting the heat pump, you do want to pay attention to the efficiency of the heat pump. And this graph just demonstrates what the cycling looks like. So the cycling due to defrost, and so this green line is the thermal output of the heat pump. And as you can see, so it's running. As it's icing up, the performance goes down actually. So the thermal output goes down, and when it's iced up too much, it goes into defrost. So the green line goes down to 0. There is no thermal output during the defrost. The blue line is the electrical input, so it's still using electricity during the defrost, but you are not getting any heat from the heat pump into the building. And when it's done with the defrost, then it's again runs in a normal operation until again it ices up too much, and the defrost happens again. So this is just to give an idea of what the cycling due to defrost looks like. And here's an example of the short cycling in the low load conditions. So that's typically in the warmer outdoor temperatures, when the heat demand of the building is too low compared to what the heat pump can supply, even with its lowest compressor speed. So like here on this bottom arm here, the thermal output is the green dots. So as you can see, it's running for roughly 5 minutes, then it's off for roughly 5 minutes, on for about 5 minutes, off for about 5 minutes. And due to these short cycles, it significantly reduces the efficiency of the heat pump. So besides that detailed monitoring that I talked about for the 3 units in Dillingham, Wrangell, and Juneau, we did a general monitoring of 30 units throughout Alaska. And it was a mix of ductless air source heat pumps, forced air ducted heat pumps, and air to water systems. And it was a mix of commercial and residential systems, and some were retrofit appliances and some were new installations. What we mean by retrofit appliances is that it's a building that's existing, has all the heating system installed in it, and then you decide to add a heat pump to it. So there'll be a retrofit situation, while new installations refers to new construction, so new buildings that you are building and are planning to install a heat pump in that building to begin with. What are the findings from that? 29 out of the 30 systems provided adequate or expected heat. There were 2 repairs needed, but both fixed at no cost to the building owner. 11 people performed maintenance on the system, just typically basic things like cleaning the filters. And 12 people used their backup heating system, even though 29 had backup heat available. So the overall message from this is that people are pretty happy with heat pumps. And that's why there's a growing interest in heat pumps in Alaska. So I mentioned that in the 2014-2015 study, even though it wasn't the purpose, we noticed that the coefficient of performance changes with different levels of thermal loading. And so that triggered a research question that we were studying recently. So recently we studied 4 different heat pumps in a cold chamber here in our building. And mainly we're looking at how the coefficient of performance is changing with the different levels of thermal loading. And here's kind of a summary of what we found out. So so when the heat pump is running at its maximum capacity with a certain coefficient of performance, if you start lowering the level of thermal loading, as you can see, the coefficient of performance goes up. but it doesn't just continue rising forever. It at a certain point reaches its peak, and then with further levels of thermal loading, it actually goes down. So this was an important observation that indicates that we can't actually give clear guidelines currently based on data that we have of sizing the heat pump systems, because as you can see, if it's undersized and it's running at maximum capacity most of the time, it's going to be a lower coefficient of performance. If it's way oversized and running at a very low capacity, it's also going to be running with a fairly low coefficient of performance. So we need to size it just right. But I should point out that this data is just based from the steady state coefficient of performance. What we really need to do is a study not in a chamber, but in the outside environment, and study the integrated coefficient of performance. So that's a study we have not been able to complete yet. But at least this gave us insight on the further steps that we need to take. And this graph here on the right, it's related to the one on the left. So on the x-axis, that's the outside temperature. On the y-axis, that's the coefficient of performance, and so the blue series is the coefficient of performance for the maximum level of thermal loading, which means on the left graph it will be this point here, and the orange series is the coefficient of performance for thermal loading close to maximum efficiency. So that will be around here, around this point. When the heat pump is not running at its maximum compressor speed, it's only partially loaded close to its peak efficiency. But again, this is just the steady state coefficient of performance. So we can't really use this to estimate the performance, the real world performance of the heat pump, because in the real world it's going to cycle. So some heat pump resources here for you. Alaska Heat Smart is an excellent resource. They're located in Juneau, but they do have some information that's applicable statewide. Then, of course, the Cold Climate Housing Research Center. Then there's this excellent tool, Alaska Municipal Heat Pump Calculator, which I'm going to demonstrate how to use in just a little bit here, that allows you to make educated decisions in your specific situation. Then there's a very new tool, so it's an interactive visualization tool to explore heat pump adoption in Alaska, developed in 2023 this year, and I'm gonna also quickly demonstrate how to use that tool. Then there are some national and also international resources. One is from the Northeast Energy Efficiency Partnership. One is this toolkit from Canada. And also, if you want to take more detailed classes on heat pumps, here are some potential classes. So Qatar and No Sun Consulting offers classes, as well as Wisdom and Associates. And also, this database, it's a national database, but it's a available database for incentives for renewable energy and energy efficiency. So here's that link for you also. So there's a message in the chat for me, and that says, I'm struggling to understand the cost benefit since I still need a normal heating system. So that's a great question. So you still have a normal heating system installed in your building, which we need in a very cold climate, like we pointed out. The heat pump stops working at a certain temperature. So we do need to have a different heating system that's going to serve as a backup. But in those temperatures, when the heat pump is actually operating, it's lowering the amount of heat that the primary heating system is supplying to the building. So if you have, say, an all-fired boiler in the building, and now you decide to also install a ductless municipal heat pump in your building, so during those temperatures, when the ductless municipal heat pump is able to operate and it's supplying heat into your building, it's lowering the amount of heat that your all-fired heating system is supplying, which means you are burning less oil. So you are burning less oil because you are providing some of the heat from the heat pump, which means you are using more electricity. And that's when it's important to understand this concept of heat pump, so we can make sure we will operate the heat pump in the conditions where the savings that you're achieving in the oil are greater than the extra energy and cost that you have because of the extra electricity consumption. Another question here in the chat about how much lower a range is the COP for a heat pump with a ducted air distribution. I'm a little hesitating to give a specific number, but you're bringing a good point that the ducted systems in general do have a lower efficiency. There's a large variations. This is actually a great tool here, is this Northeast Energy Efficiency Partnerships Cold Climate Air Source Heat Pump list, which has a number of cold climate heat pumps on it, and that includes both ducted systems as well as ductless systems. And it has various data for those heat pumps. The one you'll be likely looking at if you're looking at the efficiency is something we call the HSPF, Heating Seasonal Performance Factor, HSPF. It's actually something that relates to the coefficient of performance. The kind of tricky part nowadays with the heating seasonal performance factor is that there is a new test procedure for that, and the results of the test procedure then give you what's called HSPF2. So if you are currently using the HSPF to compare the performance of heat pumps, I just want to make this clear that there is now the HSPF2. Not all heat pumps that you'll see in the database will have the HSPF2, but the ones tested with the new procedures do. So when you're comparing it, you just want to make sure you are really comparing the same heating seasonal performance factor, because so if you can compare everything based on the HSPF2 if it's available, but you cannot compare HSPF2 from one heat pump to HSPF from a different heat pump because they were tested using different procedures, so they are not comparable. So it's now a little tricky. We are in the transition period from the two different test procedures, but as long as we are aware of that, we can still use it in a useful way like this. And so back to the fact that the ducted systems are less efficient than the ductless systems. Again, I'm going to refer you to this database to look at the exact numbers. But just to kind of give a brief idea why that is, it's likely just because the limited size of the heat exchanger. If you have a duct and you have the heat exchanger in it, you are limited by the size of the duct for the size of the heat exchanger. When you have a ductless system, you don't have the limitations of the duct. You can have a bigger heat exchanger and achieve a higher efficiency. So that's some of the reasons. Another part of the reason likely is the extra electricity needed for the fan for the ducted system, because now you are dealing with a bigger flow resistance. So you have a higher energy consumption for the fan to drive the air through the system. And I see some of you posted more resources into the chat. Thank you for doing that. Yeah, great questions. Thank you. So I'm gonna keep moving on here. So when we talk about using heat pumps to save energy, we shouldn't forget about other things we can do to save energy, because obviously the biggest savings can be achieved with a system approach where we combine a heat pump with other energy efficiency measures. So here's just an example of a super efficient home in Dillingham, Alaska, that has a heat pump installed. You can see the outdoor unit installed here. It uses a ductless mini split system, so you can see the indoor unit here. But besides having a heat pump, it's an extremely insulated building. It has 28 inches thick walls, just to kind of point out how extremely insulated it is. It is also an extremely airtight building with heat recovery ventilation. You can see the ports for the heat recovery ventilation here. Here's the intake and here's the exhaust. And just to get an idea of what kind of savings can be achieved, this building, the heating bill, the annual heating bill is a few $100s. So a few $100s annually for heating, which is a small fraction of the heating bill of typical residential buildings in Dillingham, Alaska. So again, this is just to give an idea what kind of savings you can achieve with a system approach when you combine the heat pump with strong energy efficiency measures. So how do you know if a heat pump is the right choice for you at the present time, or if there are other things that maybe you should do first to your building? So the best way to find out, or one of the best ways, I should say, is to get an energy audit. In an energy audit, an energy rater comes to your home and does an energy audit. And so the way it works is that the energy rater is gonna look probably in the attic. If you have an attic, look in your crawl space. If you have a crawl space, look at your walls and windows and take some measurements and look at the materials, and also do some testing. Often it's a blower door test to test the airtightness of the building, sometimes some additional testing, and then they are going to process all that data and come up with an energy audit report for you. And that energy audit report has a bunch of valuable information in it, but one of the things that's among them is a list of potential improvements you can make, and then list is prioritized based on their payback, with the shortest payback first. So that list allows you to see what are the most cost-effective things you can do to your building to save energy. And so based on the results, you can see if really now is a good time to install a heat pump, or if maybe you should do other things first and then install the heat pump later. So again, I would strongly recommend, if you are making decisions about improvements to your home, to hire an energy rater and get an energy audit. There's some financing and incentives available also for the installation of heat pumps, as well as other energy efficiency measures, and also some renewable energy systems. The Alaska Heat Smarts website, I showed you the link on the list of resources earlier, has a section called financing and incentives. So it's a good section I would refer you to explore. But I should also point out that currently, and that thanks to the bipartisan infrastructure law and the Inflation Reduction Act, we do have significant amounts of funding coming for energy efficiency and renewable energy, where heat pumps is actually a big portion of that. And so the Alaska Housing Finance Corporation is working diligently with the federal government on setting up the process for this funding for the renewable energy and energy efficiency systems. So stay tuned for that. So I see a question. Do you know the average cost of an energy audit? I do not know currently. I'm hesitating to give you a number. It's gonna vary, of course, based on things like the size and complexity of your building. So I'm hesitating to give you a number for an energy audit. But I would recommend either looking up an energy auditing company, or contacting the Alaska Housing Finance Corporation for that type of data. Okay, so some of the main conclusions about air source heat pumps. So as we could see, air source heat pumps can significantly reduce energy use and energy costs when used in appropriate situations and used in an appropriate way. So now, of course, the question is, so what are the appropriate situations and appropriate ways? And we looked at some of them. So there are some things where we have good answers, and there are some things where we don't have good answers yet. And like I point out, some of the research questions that we are exploring is how the efficiency changes with different levels of thermal loading. So that's a study that we did part of it in the chamber, but really to get real answers, we need similar data from a real world installation in the outside environment. So, like I said, more research is needed to gain a better understanding. And also what we learned that it's the system approach yields the biggest savings. Lots of people and entities help with these projects, so big thank yous. We couldn't have done it without them. And like I promised, I'm going to show you a couple of tools that can help you in your own decisions. So before I go to the tools, any other questions or comments? So let's see, there's a question. What would be the most efficient electric space heaters to back up the heat pump? Great question. So for the backup, I'm just gonna start from a broader perspective. So as we could see in a very cold climate, we do need a backup heating system. The backup heating system often is something like an oil-fired heating system, but it could potentially be an electric space heater. Just bear in mind that the heating with electricity is expensive. Especially in communities like Fairbanks, it's maybe a little more viable in Southeast Alaska, where the electricity comes mostly from the hydroelectric systems. But if you do choose to go with the space heater, the reality is that they all have the same efficiency. So they have a COP of 1, coefficient of performance of 1, which means they are 100% efficient. Unlike the heat pump that can have a COP of 2 or sometimes even 3, which means it's like 200 or 300% efficient. And so the reason that an electric space heater has a COP of 1, which means efficiency of 100%, is that there is no connection to the outside environment. There is no outdoor unit of a heat pump. There is no chimney. There is no connection to the outside environment. So from the law of physics, we know that energy cannot be created or destroyed. In other words, energy in equals energy out for that space heater because it has no meaningful storage in it. So all the electrical energy you put into it ends up coming out in the form of heat. That's why it is 100% efficient. So that's bear in mind when you see ads for super efficient electric space heaters and such. Bear in mind that actually they all have the same efficiency, which is 100%. There can be, of course, differences on how you use them in the space. So if you can have systems that really just provide localized service to where you are at your desk, for example, and such, then that can be that can impact the amount of energy you are going to use. But as far as the efficiency of the system itself is the same. It's 100% efficiency for any electric space heater. Any other questions? I don't see any. So let's go to these tools. So I'm going to start with the Alaska mini-split heat pump calculator developed by Alan Mitchell of Analysis North. Here's the link to it. I'm going to go to it in a little bit. I just want to point out that there are a lot of things we know about heat pumps already, and there are some things that we don't know yet, like I showed in the presentation. And so Alan, I think he did an amazing job, taking the information that we do have and coming up with the best estimate based on the information for the performance of heat pumps in Alaska. And so I'm going to go to this link and I'm going to show you how to use this tool. Then the second tool I want to show you is a newly developed tool developed this year, Heat Pumps in Alaska visualization tool developed by the University of Washington in collaboration with partners in Alaska. And it's actually partly based off of Alan Mitchell's tool, but translated into things like maps. So I'm gonna show you how to use the tool briefly afterwards. Okay, so I'm gonna stop sharing my screen here and go to a browser, and we'll get to play together with the heat pump calculator. And before I go there, I see there's a question: are there computer systems that tell the heat pump versus backup heater to operate at the best efficiency? That's a great question, because like you saw, the efficiency changes with things like different compressor speeds. The compressor speed relates to the level of thermal loading. So in theory, we could control it in a way where we would be maximizing the efficiency. And it is a research topic that researchers are looking at, but I am not aware of any commercially available system that will be able to do it for you today. That would be well developed and practical and cost effective. So it's in pretty early stages. Great question. Okay, let me stop sharing this. And I'm gonna go to a browser. And let me share my screen with you. So again, the first link, that's the Alaska Municipal Heat Pump Calculator, heatpump.analysisnorth.com. I'm gonna put in a chat actually, so everybody has that link directly. It was in the presentation. The presentation is being recorded, so you'll have that through that too. But also, let me just make sure I share this with everyone in the meeting. So here it goes to, to everyone. So Alaska Municipal Heat Pump Calculator. So again, this allows you to evaluate how effective a heat pump is in your given situation. And not only that, it also then allows you to optimize how to use the heat pump, decide things like at what temperatures do you want to be turning it off. So let's go through it together. I'm not gonna go into a lot of details just for the sake of time. The tool itself has some default values that I will mostly use for the sake of time, but we do have some items where we get to choose. Let's start with the location. So I'm gonna be seeking your input, guys. So which city in Alaska would you like me to demonstrate this tool on? Any specific interest there? Okay, I see. Anchorage, you're Homer. Great. So Anchorage was first. Let's start with Anchorage. So let's see if heat pumps make sense in Anchorage and Fairbanks, of course. I should, yeah, to be fair, I'll probably do the Fairbanks then too, because I do realize from the poll that we do have a very big group from Fairbanks here. But let's start with Anchorage, since you asked for that. So so in Anchorage, I'm choosing Anchorage. I'm just gonna select the utility rate schedule, and this is a little outdated, but not still fairly reasonable. And I'm gonna go with the default residential building. How big a building do you want? Square feet. Who wants to choose? Okay, so I see ranges from 2,500 square feet to 1,200 square feet. And the last number is a nice rounded number, 2,000 square feet. That's actually two of you there. Let's go with that then. So 2,000 square feet. I'm gonna go with the defaults, no garage, 2x6 construction, existing space heating fuel type. So in Anchorage, it's likely gonna be natural gas. So let's go with natural gas. I'm gonna go with the default price of natural gas, default efficiency of 80%. Assume a hydronic system, going with the defaults here. Now, if you do know how much your building is using, in this case, how much natural gas your building is using, and you put it here, that's gonna increase the accuracy of this model. So if you do have it, put it in. Here, we don't have it. We are just looking at a theoretical building. So you can leave it out. It's an optional item. I just want you to know that if you do have it, you'll get more accurate results. So in some communities, there's either a subsidy like the power cost equalization, or there's a block rate schedule, and that's where it would matter how much electricity you use in winter, which is when the heat pump's gonna run, versus summer, which is gonna be representative of the building itself, but not the heat pump, because the heat pump is not running. The set point, let's assume 70 degrees Fahrenheit, your set point for the indoor temperature. Let's assume a single zone unit. I'm going with the defaults here. You can actually here select the specific model of the heat pump. I'm gonna go with the default option, which is the simple option with a kind of a generic heat pump assumed here, but a very efficient one. So the heating seasonal performance factor of 14, which is one of the most efficient on the market. Install cost $4,000 looks pretty reasonable for Anchorage. Let's assume no rebates. Let's assume no financing. Let's assume the heat pump is turned off below 5 degrees Fahrenheit. Again, I'm going with the defaults here. You can play with it and use different values. You can also, some people just to keep it simple, they turn it off for the winter. So you could choose to model that scenario here. If you wanted to, I'm gonna go with the defaults, which the heat pump is on, but we will turn it off when it's below 5 degrees Fahrenheit outside. Now, is all of the buildings heat currently provided by one space heater, like a toaster or wood stove? I'm going to default no, which since we are choosing a 2,000 square foot home, is probably true, that it's not just a single system for the direct heating of the given space. Now, percentage of the home that is openly exposed to the heat pump indoor units, I'm gonna go with the default of 46%. So again, if it's a ductless mini split heat pump that is a single unit, you cannot serve the whole home that has multiple rooms. But typically you would install it in your biggest room. And then it's going to be heating for that biggest room, and for two, especially if you keep the doors open to the surrounding rooms, some of the heat is going to be serving the surrounding rooms also. But again, it's not serving the whole house. So here we're assuming it's serving 46% of the house. Now, what is your tolerance for cooler bedroom and backroom temperatures? So I'm going to go with the default of bedrooms can be as much as 5 degrees cooler than main spaces. So that way, if your heat pump is installed in one of the main spaces, and you allow the bedrooms to be as much as 5 degrees cooler, then there's some of the heat going, that's coming origin from the heat pump into the main space. Some of the heat is going into those bedrooms and heating those also. Are doors typically open to the bedrooms and backrooms that do not have a heat pump in their unit? I'm going to go with the open doors because, again, that's going to determine how much of the heat from the heat pump in the main room is going to be able to get into those bedrooms and backrooms. Sales tax, I'm going to go with the default of 0%, and let's calculate the results. Okay, rate of return not available in this case, and it's probably because this is not a cost-effective installation. So the net present value, as you can see here, is minus $11,000. So you would, over the life of the heat pump in this installation, you would be losing roughly $11,000. And we're still gonna look at the breakdown here. You're gonna be saving natural gas. This is how much natural gas you're gonna save, but you're gonna be using more electricity. And because of the relatively cheap natural gas in Anchorage, this is why this is not a cost-effective installation. That the extra cost because the electricity is greater than the savings in the natural gas. Seasonal average heat pump COP of 2.5. So that also indicates we are likely going to have savings in greenhouse gas emissions. We do, because this is a pretty good COP. So even though it's not cost effective, this installation is going to be saving greenhouse gas emissions. So the extra greenhouse gases from the electricity that you need for the heat pump are going to be less than the greenhouse gases that you are saving by burning less natural gas. Results by month. Here, the blue part indicates how much heat is coming from the heat pump. The red part, how much is coming from the existing, in our case, natural gas system. The reason it's not as much in months like January is because when you have temperatures below 5 degrees Fahrenheit, we chose in here that heat pump is not going to be running, unlike months like March, where it's warmer outside, so the heat pump is going to be running a bigger portion of the time. So as you can see in Anchorage, you can a very large portion of the heating load can come from the heat pump. But also when you look at the cost, every month you are losing money. So so here if you are saving money, you would see some green portions here. We don't. We only see the red portions where the cost is increasing. So so the black dots is the baseline energy cost, but now because of the heat pump, our overall cost is higher. So again, the cost for the electricity is greater than the savings in the cost of the natural gas. So that's Anchorage, and it's kind of a known fact that in a typical situation, Anchorage currently heat pump is not cost effective. Doesn't mean we should forget about heat pumps in Anchorage. As you could see, there are greenhouse gas emission savings thanks to heat pumps. There might be potential incentives coming for heat pumps. So the situation might change. But if you're in Anchorage currently, and if the main thing you're looking at is the money, as you can see in a typical situation, it's not a cost-effective installation. Also, heat pumps are getting better. Another thing I should point out. So again, this doesn't mean you should forget about them, but this again means that currently it's not cost effective, but there are certain things in the future that might turn out to be to change this conclusion. Natural gas prices might go higher. Also, you can be balancing out how much you are going to be using the heat pump, in deep winter versus in the shoulder seasons. You can see in the warmer months, the loss here is getting lower. So those are the types of thing you would play with as the factors are changing. So that's Anchorage. Now let me catch up on the questions here. We are going to build a 2,000 square foot greenhouse in Anchorage and are considering a heat pump system for shoulder season use. Is it practical? Again, I'll let you play with this tool for your situation to make that decision. Thank you. And another question: we have solar panels and net metering in Fairbanks. Does this calculator allow for that in its calculations? So that's a great question. So when you have solar panels, is it gonna change the economics of heat pumps? And this calculator does not allow to model it directly because now what it depends on is how much are going to be those situations when the heat pump is drawing the energy at the same time when the solar panels are producing it. So in that situation, your solar panels are supposed to feeding into the grid, and you getting paid less for that. They actually utilized on site with your heat pump, and your savings are more because how much you are paying per kilowatt hour is more than how much you get paid if you are feeding the energy back into the grid. So how much of those situations are going to be compared to those situations when the solar panels are producing, but heat pump is not drawing anything, and then the heat pump is drawing energy when the solar panels are not producing much. And the reality is that we mostly need the heat in winter. and we don't get that much sun in winter. It's not completely that way, because months like March, for example, you do get a good amount of sun and you still have some heating needs. So they do overlap a little bit, but there is not a perfect alignment between when you need a heat pump and when you have the solar resource available, unfortunately. But again, back to the exact numbers. This specific calculator here does not have the function to fully consider those numbers. Great question. So let's switch this to Fairbanks now, because again, you guys asked for it, and we do have a large population from Fairbanks here. Okay, so here is Fairbanks, and we'll use here Golden Valley Electric Association residential rate. Again, this is not totally up to date, but it's still fairly representative of the current situation. And I'm gonna leave everything else the same. So residential building, 2,000 square feet, no garage, 2x6 construction. Well, I'm not gonna leave everything the same. Sorry. In Fairbanks, a more common situation would be using #1 heating oil. So I'm gonna change it to that. 4.59 per gallon here. Again, not totally up to date, but I think still fairly reasonable. Standard heating system, 80% efficient, hydronic. We don't have actual data to put here, but if you did, you would, to calibrate the model better. I'm gonna go with the same values we used before here for electricity use. Set point 70 degrees Fahrenheit, single zone system. We are using this generic model with 14 HSPF, the heating seasonal performance factor. As you can see, the installation in Fairbanks is more expensive than in Anchorage. That makes sense. Still a pretty reasonable price. It varies, of course, on the specific installation. Every house is different, and there are going to be different access to your existing electrical system, and different penetrations to the walls and such. So this is just giving you kind of an average value. Your house might be different than that, but typically, a typical value in Fairbanks is about $5,000 installed for a ductless mini split system. No rebates, no financing. Let's again turn it off below 5 degrees Fahrenheit. 46% exposed to the heat pump. We can tolerate as much as 5 degrees cooler in bedrooms. Open doors, no sales tax, and let's calculate the results. And now, as you can see, Fairbanks is a very different situation than Anchorage. It, on one hand, is a little counterintuitive, right? Anchorage is much warmer, so heat pumps should work better there, and that's true. But Anchorage has that relatively cheap natural gas that Fairbanks does not. And that's what significantly changes the economics. So, a very good rate of return, 13.7%, net present value, over $3,000. So significant savings over the life of the heat pump. Saving annual heating fuel savings, significant savings. In the heating oil, of course, you are going to use more electricity now that you have the heat pump, but the cost of that electricity is less than the savings in the cost of the heating oil. COP of, again, about 2.5, and greenhouse gas emissions. I should point out this calculator is based on the average fuel mix in Fairbanks, which has some coal in it, but the current situation in Fairbanks, like I pointed out earlier, based on my understanding at least, is that you are not going to be increasing the consumption of coal when you install a heat pump, because it's already maxed out. So so you can put in manual inputs actually for the CO2 emissions. You could do it all the way all the way up here. Advanced utility. inputs, I believe, in that section. And we did do the math. So with the math, we concluded that break-even point is about COP of 2. So with 2.5, you're actually saving greenhouse gases even in Fairbanks. But this tool does not have the capacity to reflect that. Again, this tool goes based on the average fuel mix in Fairbanks. So results by month. So here again, the blue is the heat supply from the heat pump, while the red is the heat supply from the existing system. In Anchorage, you could see that most of the graph was blue. So really, the majority of the heating was provided by the heat pump. Here in Fairbanks, it's not as much that way. Here we see a lot more of the red. And obviously, it's because Fairbanks is a lot colder. So we have a lot more of those situations when the heat pump is not running and your other heating system is supplying the heat. Here you can see every month you are saving money. So every month here is in green. So every month the savings in your heating oil are greater than the extra cost you are paying for that extra electricity that the heat pump needs. And so now I should also demonstrate how you can then, besides just determining if the heat pump is suitable for your specific situation, then you can also use it to help you optimize how you use it. So for example, let's say what happens if we use it all the way down to 0 degrees Fahrenheit as opposed to 5 degrees Fahrenheit. So you can change that, and let's just kind of remember, the savings here. So 13.7% and about $3,000 net present value. And I'm going to change this, and let's use it all the way down to 0 degrees Fahrenheit. And we are going to recalculate the results. And this was an efficient heat pump, again, 14 HSPF. It's among the top, and because of that, even down to those 0 degrees Fahrenheit, it's actually operating a beneficial operation. We can see that because the rate of return increased even further, and the net present value, which means the savings for the life of the heat pump, also increased from the previous value. And I should say, the net present value is a little more than just the direct savings. They take the time value of money into account, which would be like if you are borrowing money, that would be the interest rate from the bank. But this is a significant number, so significant savings by using a heat pump in Fairbanks in the current situation that we have. So that's I'm not gonna go into these details anymore. I explained what those mean, but that's in a nutshell how you could use this tool to make educated decisions in your given situation. So let me catch up on the questions here. So it says, it seems most HVAC refrigeration professionals lack the training and knowledge to install these air source heat pump and splits. Is that the case? It is the case that there's a lot of demand for heat pumps, and the workforce is lacking. So that's also something that the state of Alaska is working on to train the workforce for the installation and maintenance of heat pumps in Alaska. Yes, that is the current situation. Okay, so I don't see any other questions, and I know we are pretty close to the end here. So, and I promised I'm going to show you one more tool. So I'm gonna go to it right here. So this right now was the ductless mini split heat pump calculator to help you evaluate in your specific situation if a heat pump makes sense or not, and also how we can optimize it in that situation. Now the other tool does not gonna relate to your specific situation. It's gonna use a typical household to give you some ideas about the benefits of heat pumps in Alaska. So it's the Alaska heat pump visualization tool. I'm gonna copy paste that address again for you here. Developed, it's by the data science for social good initiative or program at the University of Washington. And I'm gonna give you the link here. I'm gonna make sure it's going to everyone. And I know there are some questions now. I'll try to catch up on them towards the end of the session based on the time. Just want to make sure we cover this tool here. Sorry about that. So again, it's an interactive visualization tool to explore heat pump adoption in Alaska. I should point out that the maps they are using in this tool are modified to reflect population. So, Anchorage, the normal map, for example, is just a dot on a map, while Anchorage is the biggest population center in Alaska. So here they use a modified map that reflects the population. So here Anchorage, has the biggest area of the map because it's the biggest population center. So just so when you see the maps in this tool, so you know why it is the way it is. And this tool has a number of functions here, but I just want to point out one, and that's the economic feasibility. So I went to the borrow potential and economic feasibility of heat pumps. And you can actually also make some projections here for fuel price increases. It does not have the current scenario, but I'm just going with the 3%, which is the closest to the current scenario. And also you can here model different subsidies. I'm going to go with no subsidy here as a default value. But what this is a good starting point, not necessarily for your specific situation, but if you just want to see where in Alaska heat pumps make sense, this is a good map to look at, kind of, just before you start spending a lot of time on doing a research for your specific situation, you're just wondering, okay, do heat pumps in general make sense in my area? So this is a map that you can look at that gives you that idea. So this tool actually uses that calculator that we just looked at to do these calculations. But here you have it all summarized for a number of different regions, the results of that, and typical households. So this gives you the net present value, so it'll be the savings over the life of the heat pump, where blue is positive numbers, which means that's where you are saving money. Red is the negative numbers, that's where you're losing money. We just confirmed what coincidentally you guys asked for in the tool a little while ago, because when we Anchorage, we saw you're losing money. And here, yeah, it's confirmed. It's in red. We are losing money. We did Fairbanks, and you see you are saving money. And here we confirm it also. Fairbanks is in blue. You are saving money. So I just wanted you to be familiar with this tool. It's a brand new tool developed now in 2023, and you have the link for that. So I'm gonna pause here, and let me quickly catch up on your questions here. Okay, we currently have an old boiler with baseboard heaters. Any way to tie in the two systems? So that's a great question. When you have a boiler, a kind of initial idea for most people is to, can I just replace it with an air-to-water heat pump? And the answer is it's not easy. So for one, you would lose your backup heat source if you if you just replace it, and you do need backup heat source in places like Fairbanks. But for two, even if you are able to maintain it as a backup system, the boilers and installation of boilers in current buildings are typically designed in a way that they need high temperatures. Typically, they use baseboard heating elements, and they do need high temperatures of the distribution fluid. And the high temperature of the distribution fluid, if you try to achieve with a heat pump, it's gonna, for one, significantly lower the efficiency because the higher temperature lift the heat pump needs to make, the lower the efficiency. And for two, you might not even find a model of a heat on the market that would actually be able to make such a temperature lift. So it is challenging to actually replace or at least supplement boiler installations in very cold climates with air-to-water heat pumps. It's not impossible. There are some solutions that we have been thinking of. One solution is to do an envelope retrofit at the same time. So if you can do an energy efficiency retrofit and make the heat pump, make the building a lot more efficient at the same time, all of a sudden you need a lower temperatures for your delivery fluid, and the heat pump might start actually making sense for that. So there are potential options, but again, it's not a straightforward solution. Is a 100 amp house panel enough for a heat pump? It depends. So the installer will need to evaluate that. It depends on how much it's already loaded and depends on the size of the heat pump you're going to be looking at. Do you see that heat pumps differ in performance between different manufacturers? There are different there's different performance for different heat pump models, like you could see in the study that we did in 2014, 2015. I don't want to necessarily tie it to a given manufacturer, because a given manufacturer also produces a range of efficiencies of their heat pumps. So you can have the same manufacturer, can have a really efficient heat pump, or you can have a fairly inefficient heat pump from the same manufacturer. It says Fairbanks gets hot in summer and most don't have air conditioning. I'll be interested in a two-way heat pump. I'm glad you posted this question because it's important to know that, like the ductless mini split system with just a press of a button switches from heating to cooling. So it has a reversing valve and it just reverses the operation. So that's one of the advantages of heat pumps, that you can easily use it for cooling also. The installation needs to have a drain, because then there can be condensation on the indoor unit when you are cooling the indoor air. So you need to make sure you have the drain connected, so it just doesn't like drip on the floor or something, damage something. So you need to pay attention to it for the installation. But assuming it is installed correctly, it's just a switch of a button to switch from heating to cooling. And I think this is perfect timing because I hope I have covered all the questions, and we have about 2 minutes to spare. So thank you very much. And Rosa, I'm handing it over back to you.
Thank you so much, Tom. That was really informative and I learned so much, and I thank you so much for presenting.